Welcome to Spelling Bee Ninja. I'm thrilled to have you join us today for an engaging episode all about chemical reactions. Whether you are in middle school or high school, understanding chemical reactions is fundamental to grasping the principles of chemistry and how the world around us works. Today, we will explore the various types of chemical reactions, how they occur, and what signs to look out for. So grab your notebooks and get ready to dive into the fascinating world of chemical transformations. Let's begin by understanding what a chemical reaction is. A chemical reaction is a process in which substances called reactants undergo transformations to become different substances known as products. These transformations involve the breaking and forming of bonds between atoms. Throughout this process, the atoms are rearranged, but it's important to remember the law of conservation of mass, which states that no atoms are created or destroyed. This means that the mass of the reactants will equal the mass of the products. As we learn about chemical reactions, there are several signs that indicate a reaction has taken place. These signs can include a color change, a temperature change, the production of gas, the formation of a solid, or the emission of light. Think of how a color change can signify that something new is happening when you mix baking soda and vinegar to produce carbon dioxide gas. What a delightful example of a chemical reaction! Now, moving to the next concept, we have reactants and products. In every chemical reaction, we start with reactants. For instance, when hydrogen gas and oxygen gas combine, they react to form water. In this equation, hydrogen and oxygen are the reactants, while water is the product. It's fascinating to note that the arrow in a chemical equation indicates that one side produces the other. In more dramatic reactions, such as when vinegar and baking soda combine, you can see the bubbles forming due to the produced carbon dioxide. This moment beautifully illustrates chemistry in action. Next up, let's discuss energy changes which play a vital role in chemical reactions. We categorize reactions based on energy exchange into exothermic and endothermic reactions. An exothermic reaction releases heat energy, making the surroundings feel warm. Classic examples include combustion reactions, like burning wood or natural gas. Conversely, endothermic reactions absorb heat energy, causing a drop in temperature. An everyday example of this is when ice melts. The process takes in heat energy from the surroundings, creating a cooling effect. Understanding these energy changes can help us appreciate why certain reactions are used in everyday life, like self-heating cans of food that utilize exothermic processes. Now, let's shift our focus to combustion reactions in particular. Combustion is an exothermic reaction that occurs when a substance typically containing carbon, such as hydrocarbons, rapidly reacts with oxygen to produce heat, light, carbon dioxide, and water. For instance, when you light a candle or burn fuel, a combustion reaction occurs. This reaction requires three essential components, often referred to as the fire triangle: fuel, oxygen, and heat. Removing one of these components can extinguish the fire, which is a crucial concept in fire safety. Now let's pivot to a different, but equally exciting area: oxidation-reduction reactions, more commonly known as redox reactions. These reactions involve the transfer of electrons between substances. Oxidation refers to the loss of electrons, while reduction refers to the gain of electrons. A helpful mnemonic to remember this is oil rig, which stands for oxidation is loss, reduction is gain. One familiar example of an oxidation reaction is rusting, where iron combines with oxygen to form iron oxide. This simple process highlights the intricate balance of chemical reactions in our environment. Moving on, we enter the world of synthesis reactions. Synthesis, or combination reactions, occur when two or more simple substances combine to form a more complex product. The general pattern for these reactions is a plus B yields AB. One classic example is the reaction between hydrogen and oxygen to create water. Another example can be seen in the creation of table salt, sodium chloride, which happens when sodium combines with chlorine gas. These reactions can be exothermic, meaning they release energy, making them significant in various chemical processes. Next, let's explore decomposition reactions. This type of reaction is fascinating because it involves breaking down a complex compound into simpler substances. The general form is AB yields A plus B. You can see decomposition reactions when water is split into hydrogen and oxygen gas through electrolysis. Similarly, when calcium carbonate, commonly known as limestone, is heated, it breaks down into calcium oxide and carbon dioxide. What's particularly intriguing about decomposition reactions is that they often require an energy input, such as heat, electricity, or light, to initiate the reaction. This energetic requirement takes us to our next topic, single replacement reactions. In these reactions, a more reactive element displaces a less reactive element from a compound. The general equation for a single replacement reaction can be represented as A plus BC yields AC plus B. A well-known example is when zinc displaces copper from copper, 2-sulfate, forming zinc sulfate and free copper. Understanding the reactivity series of metals can help predict whether such reactions will occur, making this concept essential for budding chemists. Next, we will consider double replacement reactions, where two compounds exchange ions or elements to form two new compounds. The pattern can be written as AB plus CD yields AD plus CB. A common example involves silver nitrate and sodium chloride coming together to produce silver chloride and sodium nitrate. This reaction demonstrates how ions can swap places to form entirely new chemical species. These types of reactions are often encountered in neutralization reactions where an acid and a base react together to form salt and water. Learning to identify these reaction types opens up avenues for further exploration in chemistry. Finally, let's touch on the role of catalysts in chemical reactions. A catalyst is a remarkable substance that accelerates a reaction without being consumed or altered in the process. Catalysts work by lowering the activation energy necessary for a reaction to take place. This characteristic is critically important in both natural and industrial processes. For instance, biological catalysts known as enzymes speed up reactions within our bodies, allowing us to digest food efficiently. In industry, catalysts help improve processes, like the catalytic converters in cars that convert harmful gases into less harmful substances. Fascinatingly, catalysts can change the pace of chemical reactions in ways that are vital for sustainable practices. To recap, we've explored various facets of chemical reactions today, including the transformation of reactants into products, the signs of reactions, energy changes, and the importance of different reaction types such as synthesis, decomposition, and replacement reactions. We also examined the critical role of catalysts in speeding up chemical processes. These concepts build a fundamental understanding of how matter interacts in the world, paving the way for further exploration of chemistry in both everyday life and scientific endeavors. Remember, chemistry is not just a set of rules but an intricate dance of atoms and molecules that shapes our universe. Thank you for joining us today on this journey into the world of chemical reactions. We hope you found this lesson engaging and enlightening. As you continue to explore the wonders of chemistry, keep asking questions and seeking answers. If you enjoyed this episode, be sure to tune in for our next lesson where we'll explore more exciting topics in science. Until next time, keep your curiosity alive and never stop learning.